In the earlier modules, we have learned that the element carbon has the unique property called catenation, due to which it forms covalent bonds with other carbon atoms. It also forms covalent bonds with atoms of other elements like hydrogen, oxygen, nitrogen, sulfur, phosphorus, and halogens. The resulting compounds are studied under a separate branch of chemistry called organic chemistry. Introduction. Organic compounds are vital for sustaining life on Earth and include the complex molecules like the genetic information bearing deoxyribonucleic acid or DNA, and proteins that constitute essential compounds of our blood, muscles, and skin. Organic chemicals appear in materials like clothing, fuels, polymers, dyes, and medicines. The science of organic chemistry is about 200 years old. Around the year 1780, chemists began to distinguish between organic compounds obtained from plants and animals and inorganic compounds prepared from mineral sources. Berzelius, a Swedish chemist, proposed that a vital force was responsible for the formation of organic compounds. However, this notion was rejected in 1828 when F. Buhler synthesized an organic compound, urea, from an inorganic compound, ammonium cyanate. The reaction is as shown here. The pioneering synthesis of acetic acid by Coolby in 1845 and that of methane by Berthelot in 1856 showed conclusively that organic compounds could be synthesized from inorganic sources in a laboratory. The development of electronic theory of covalent bonding ushered organic chemistry into its modern shape. Tetravalence of carbon. Shapes of organic compounds. The shapes of carbon compounds. The knowledge of fundamental concepts of molecular structure helps in understanding and predicting the properties of organic compounds. You have already learned the theories of valency and molecular structure in the earlier modules. Also, you already know that the tetravalence of carbon and the formation of covalent bonds by it are explained in terms of its electronic configuration and the hybridization of s and p orbitals. It may be recalled that the formation and the shapes of molecules like methane, CH4, ethene, C2H4, ethyne, C2H2, are explained in the terms of the use of sp3, sp2, and sp hybrid orbitals by carbon atoms in the respective molecules. It is very important to note that hybridization influences the bond length and bond enthalpy or strength in organic compounds. The sp hybrid orbital contains more s character and hence it is closer to its nucleus and forms shorter and stronger bonds than the sp3 hybrid orbital. The sp2 hybrid orbital is intermediate in s character between sp and sp3, and hence the length and enthalpy of the bonds it forms are also intermediate between them. The change in hybridization affects the electronegativity of carbon. The greater the s character of the hybrid orbitals, the greater is the electronegativity. Thus, a carbon atom having an sp hybrid orbital with 50% s character is more electronegative than that possessing sp2 or sp3 hybridized orbitals. This relative electronegativity is reflected in several physical and chemical properties of the molecules concerned, about which we will learn in the later modules. Isomerism, Part 1. In this module, let us understand about the concept of isomerism. By definition, the phenomenon of existence of two or more compounds possessing the same molecular formula but different properties is known as isomerism. Such compounds are called as isomers. Let us study about structural isomerism. In the structural isomerism, the compounds having the same molecular formulae but different structure, that is, the way the atoms are arranged, are classified as structural isomerism. Now, there are different types of structural isomerisms. Let us first understand chain isomerism. When two or more compounds have similar molecular formulae but different carbon skeletons, these are referred to as chain isomers, and the phenomenon is termed as chain isomerism. Let us take this example. C5H12 can be represented by three compounds. The first compound is pentane. This is a straight chain, as you can clearly see. All the carbon atoms are arranged in a straight chain. The second compound is isopentane or 2-methylbutane. Here you can clearly see that one carbon atom is attached with the second carbon atom of the straight chain, thus forming a different carbon skeleton. The third compound is neopentane. Here you can find two carbon atoms attached to the second carbon atom, forming a different carbon skeleton. Hence, you can see, although all the three compounds have same molecular formulae, C5H12, yet each differs by their different skeleton structure. Isomerism, Part 2. Now let us learn about the next type of structural isomerism. Position isomerism. When two or more compounds differ in the position of substituent atom or functional group on the carbon skeleton, they are called position isomers, and this phenomenon is termed as position isomerism. For example, the molecular formula C3H8O represents two alcohols, propan 1-ol and propan 2-ol. The position of functional group OH is different in both the cases. Hence, both are position isomers of C3H8O. The next type of structural isomerism is functional group isomerism. Functional group isomerism. Two or more compounds having the same molecular formula but different functional groups are called functional isomers, and this phenomenon is termed as functional group isomerism. For example, C3H6O represents an aldehyde and a ketone, that is, propanone and propanal. Hence, both propanone and propanal are functional group isomerism of C3H6O. Now let us learn about metamerism. Metamerism arises due to different alkyl chains on either side of the functional group in the molecule. For example, C4H10O represents methoxypropane, CH3OC3H7, and ethoxyethane, C2H5OC2H5. As you can see here, the two different compounds differ by different alkyl groups around the central functional group. Nomenclature of organic compounds having functional group. Part 1. A functional group, as defined earlier, is an atom or a group of atoms bonded together in a unique manner, which is usually the site of chemical reactivity in an organic molecule. Students, it is very important to note that compounds having the same functional group undergo similar reactions. For example, CH3OH, CH3CH2OH, and CH3CHOH, all having OH functional group, liberate hydrogen on reaction with sodium metal. The presence of functional groups enables systematization of organic compounds into different classes. Here you can see some functional groups with their prefixes and suffixes, along with some examples of organic compounds possessing these. Let us take the example of CH3, CH2, CH2, CH2OH. First of all, the functional group present in the molecule is identified, which determines the choice of appropriate suffix. The longest chain of carbon atoms containing the functional group is numbered in such a way that the functional group is attached at the carbon atom possessing lowest possible number in the chain. As in this case, OH attached to the carbon atom has number 1 and not number 4. Hence, the second case would be a wrong way of naming the compound. By using the suffix as shown here, the name of the compound is arrived at. For example, butan-1-OL. In case of the polyfunctional compounds, one of the functional groups is chosen as the principal functional group, and the compound is then named on that basis. The remaining functional groups, which are subordinate functional groups, are named as substituents using the appropriate prefixes. Let us take this example, HOCH2, CH2, whole 3, CH2, COCH3. Here, this compound is named as 7-hydroxyheptan 2-on as ketone group has been named as the principal functional group, and OH group has been named as the subordinate group. Now, do you know why ketone group has been preferred over hydroxyl group? Nomenclature of organic compounds having functional group. Part 2. The choice of principal functional group is made on the basis of order of preference. The order of decreasing priority for some functional groups is as shown here. Here you can see that the carboxylic group has been given the topmost priority and C triple bond has been allocated the lowest priority. This priority is taken care of when the compounds are named. It is very important to understand the R, halogens, F, Cl, Br, I, NO2, alkoxy, OR, etc. are always prefix substituents. Thus, a compound containing both an alcohol and a keto group is named as hydroxyalkanone, since the keto group is preferred to the hydroxyl group. And is named as 7-hydroxyheptane 2-on and not as 2-oxoheptane 7-OL. Similarly, BRCH is named as 3-bromoprop 1-ene and not 1-bromoprop 2-ene. As already discussed, halogens are prefix substituents and not concerned with the priority. If more than one functional groups of the same type are present, their number is indicated by adding di, tri, etc. before the class suffix. In such cases, the full names of the parent alkane is written before the class suffix. For example, CH2OH, CH2OH is named as ethane 1,2-diol. However, the ending Ne of the parent alkane is dropped in the case of compounds having more than one double or triple bond. For example, CH2 bond CH bond CH2 is named as buta-1,3-diene. Classification of organic compounds. Part 1. Classification of organic compounds. The existing large number of organic compounds and their ever-increasing numbers has made it necessary to classify them on the basis of their structures. Organic compounds are broadly classified as shown. Organic compounds are divided into two parts. 1. Acyclic or open-chain compounds, and 2. Cyclic or closed-chain or ring compounds. Further, cyclic or closed-chain or ring compounds are divided into two parts as shown. 1. Homocyclic or carbocyclic compounds, and 2. Heterocyclic compounds. Further, homocyclic or carbocyclic compounds are divided into two parts as shown. 1. Alicyclic compounds, and 2. Aromatic compounds. First of all, let us see acyclic or open-chain compounds. These compounds are also called as aliphatic compounds and consist of straight or branched chain compounds. For example, ethane, isobutane, acetaldehyde, and acetic acid. Now let us see alicyclic or closed chain or ring compounds. Alicyclic or aliphatic cyclic compounds contain carbon atoms joined in the form of a ring or homocyclic. Sometimes atoms other than carbons are also present in the ring, that is heterocyclic. Some examples of these types of compounds are cyclopropane, cyclohexane, cyclohexene, and tetrahydrofuran. These exhibit some of the properties similar to those of aliphatic compounds. Aromatic compounds. Aromatic compounds are special types of compounds. Like alicyclic compounds, aromatic compounds may also have heteroatom in the ring. Such compounds are called heterocyclic aromatic compounds. Some of the examples of various types of aromatic compounds are benzoid aromatic compounds like benzene, aniline, and naphthalene. Other examples of aromatic compounds are non-benzoic compounds like tropolone and heterocyclic aromatic compounds like furan, thiophene, and pyridine. Here you can clearly see that these compounds also contain atoms other than carbon and hydrogen. As in case of furan, you have oxygen atom in addition to hydrogen and carbon. Classification of organic compounds. Part 2. Organic compounds can also be classified on the basis of functional groups into different families or homologous series. In organic chemistry, there is another important concept of functional group, Before moving any further, let us define functional group. The functional group may be defined as an atom or group of atoms joined in a specific manner which is responsible for the characteristic chemical properties of the organic compounds. The examples are shown as hydroxyl group OH, aldehyde group CHO, and carboxylic acid group COOH, etc. Related to the functional group is the functional series. A group or a series of organic compounds, each containing a characteristic functional group, forms a homologous series, and the members of the series are called homologues. The members of a homologous series can be represented by general molecular formula, and the successive members differ from each other in molecular formula by a -CH2 unit. There are a number of homologous series of organic compounds. Some of these are alkanes, alkenes, alkynes, etc. IUPAC Nomenclature of Alkanes. Part 1. In this module, let us learn about the IUPAC nomenclature of alkanes. First of all, let us understand the straight-chain hydrocarbons. The name of such compounds are based on their chain structure and end with suffix -ane and carry a prefix indicating the number of carbon atoms present in the chain, except from CH4 to C4H10, where the prefixes are derived from trivial names. The IUPAC names of some straight-chain saturated hydrocarbons are given here in the table. If you notice, you will find that the alkanes in table differ from each other by merely the number of -CH2 groups in the chain. They are homologues of alkane series. Now let us study about the branched chain hydrocarbons. In a branched chain compound, small chains of carbon atoms are attached at one or more carbon atoms of the parent chain. The small carbon chains or branches are called alkyl groups. Some examples of these are shown here, like in this case of 2-methylbutane. Here, one methyl group is attached with the butane, which is a parent chain. And similarly in the case of 2-ethyl 3-methylpentane. Here, ethyl and methyl groups are attached with the pentane, which is a parent chain. In order to name such compounds, the names of alkyl groups are prefixed to the name of the parent alkane. For example, in 2-methylbutane, where methyl is the attached group to the main parent alkane butane. An alkyl group is derived from a saturated hydrocarbon by removing a hydrogen atom from carbon. Thus, CH4 becomes -CH3 and is called methyl group. An alkyl group is named by substituting YL for ANE in the corresponding alkane. For example, in 2-methylbutane, where methane group is attached to the main parent alkane, it is abbreviated as methyl. Some alkyl groups are listed in the table shown here. Here, methane's corresponding alkyl group is methyl. Similarly, ethane's corresponding alkyl group is ethyl, and so on. IUPAC Nomenclature of Alkanes, Part 2. Abbreviations are used for some alkyl groups. For example, methyl is abbreviated as Me, ethyl as Et, propyl as Pr, and butyl as Bu. Thus, propyl and butyl groups can have branched structures as shown here. For example, isopropyl, secondary butyl, isobutyl, tertiary butyl, and neopentyl. Common branched groups have specific trivial names. For example, the propyl groups can either be N-propyl group or isopropyl group, based on the position of carbon atoms. The branched butyl groups are called secondary butyl, isobutyl, and tertiary butyl group. We also encounter the structural unit CH2CCH3 which is called neopentyl group. IUPAC Nomenclature of Alkanes, Part 3. Nomenclature of branched chain alkanes. We encounter a number of branched chain alkanes. Now let us understand the rules for naming branched chain alkanes by this example. The rules for naming them are: 1. First of all, the longest carbon chain in the molecule is identified. In the example, the longest chain has 9 carbons and it is considered as the parent or root chain. Selection of the parent chain as shown in 2 is not correct because it has only 8 carbons. So the rule says, find the longest carbon chain in the molecule. Now, after identifying the longest chain, the next step is: 2. The carbon atoms of the parent chain are numbered to identify the parent alkane and to locate the position of the carbon atoms at which branching takes place due to the substitution of alkyl group in place of hydrogen atoms. The numbering is done in such a way that the branched carbon atoms get the lowest possible numbers. Thus, the numbering in the shown example should be from left to right, branching at carbon atoms 2 and 6 and not from right to left, giving numbers 4 and 8 to the carbon atoms at which branches are attached. In the next step, 3, the names of alkyl groups attached as a branch are then prefixed to the name of the parent alkane, and the position of the substituents is indicated by the appropriate numbers. If different alkyl groups are present, they are listed in alphabetical order. Thus, the name for the compound shown is 6-ethyl 2-methylnonane. Note, the numbers are separated from the groups by hyphens, and there is no break between methyl and nonane. Also, in some cases, if 2 or more identical substituent groups are present, then the numbers are separated by commas. The names of identical substituents are not repeated. Instead, prefixes such as di for 2, tri for 3, tetra for 4, penta for 5, hexa for 6, etc. are used. While writing the name of the substituents in alphabetical order, these prefixes, however, are not considered. As in the case of 3-ethyl 4,4-dimethylheptane. Here, ethyl has been put before methyl in the alphabetical order, despite methyl having the prefix as di. Also, it is very important to know that if 2 substituents are found in equivalent positions, the lower number is given to the one coming first in the alphabetical listing. Thus, the following compound is 3-ethyl 6-methyloctane and not 6-ethyl 3-methyloctane. So in this case, ethyl comes first in the alphabetical order as compared to methyl, hence ethyl has to be given a lower number. The branched alkyl groups can be named by following the above mentioned procedures. However, the carbon atom of the branch that attaches to the root alkane is numbered 1, as shown here in 1,3-dimethylbutyl. Nomenclature of organic compounds. In this module, let us understand about the nomenclature of organic compounds. Organic chemistry deals with millions of compounds. In order to clearly identify them, a systematic method of naming has been developed and is known as the IUPAC, or International Union of Pure and Applied Chemistry System of Nomenclature. In this systematic nomenclature, the names are correlated with the structure such that the reader or listener can deduce the structure from the name. Before the IUPAC system of nomenclature, however, organic compounds were assigned names based on the origin or certain properties. For instance, citric acid is named so because it is found in citrus fruits, and the acid found in red ant is named formic acid, since the Latin word for ant is formica. These names are traditional and are considered as trivial or common names. Some common names are followed even today. For example, Buckminster fullerene is a common name given to the newly discovered C60 cluster, a form of carbon noting its structural similarity to the geodesic domes, popularized by the famous architect R. Buckminster Fuller. Common names are useful and in many cases indispensable, particularly when the alternative systematic names are lengthy and complicated. Common names of some organic compounds are given here in the table. So, compound CH4 has the common name of methane. C4H10 has the common name of N-butane, and so on. The IUPAC system of nomenclature. In the IUPAC system of nomenclature, a systematic name of an organic compound is generally derived by identifying the parent hydrocarbon and the functional groups attached to it. Let us see this example. Here you can see a compound containing a functional group, containing a branch, and also you can see the parent chain of the compound. Before understanding about IUPAC any further, one needs to understand some key terms. Compounds containing carbon and hydrogen only are called hydrocarbons. A hydrocarbon is termed saturated if it contains only carbon-carbon single bonds. The IUPAC name for a homologous series of such compounds is alkane. Unsaturated hydrocarbons are those which contain at least one carbon-carbon double or triple bond. The IUPAC name for a homologous series of such compounds is alkene and alkyne respectively. Nomenclature of substituted benzene compounds. Part 1. Nomenclature of substituted benzene compounds. Now let us understand about the IUPAC nomenclature of substituted benzene compounds. In substituted benzene compounds, the substituent is placed as prefix to the word benzene, as shown in the following examples, like methylbenzene, methoxybenzene, aminobenzene, nitrobenzene, and bromobenzene. For example, in the case of bromobenzene, the substituent bromine is placed as prefix to the word benzene as bromobenzene. However, common names written in the bracket below of many substituted benzene compounds are also universally used. If the benzene ring is di-substituted, the position of substituents is defined by numbering the carbon atoms of the ring, such that the substituents are located at the lowest numbers possible. For example, the compound shown is named as 1,3-dibromobenzene and not as 1,5-dibromobenzene. Here, since position 3 is a lower number position as compared to position 5, in the trivial system of nomenclature, the terms meta, M, ortho, O, and para, P, are used as prefixes to indicate the relative positions 1, 3, 1, 2, and 1, 4 respectively. Thus, 1,3-dibromobenzene is named as meta-dibromobenzene. Similarly, 1,2-dibromobenzene is named as ortho-dibromobenzene, and 1,4-dibromobenzene is named as para-dibromobenzene, respectively. Nomenclature of substituted benzene compounds, Part 2. For tri- or higher substituted benzene derivatives, these prefixes cannot be used, and the compounds are named by identifying substituent positions on the ring by following the lowest locant rule. In some cases, the common name of benzene derivatives is taken as the base compound. Substituent of the base compound is assigned number 1, and then the direction of numbering is chosen such that the next substituent gets the lowest number. The substituent appears in the name in alphabetical order. In this case, the name of the compound will be 2-chloro-1-methyl 4-nitrobenzene and not 4-methyl 5-chloronitrobenzene. Hope you can understand why we have numbered chlorine at position 2 instead of position 5. Let us see another example. This compound would be named as 1-chloro-2-4-dinitrobenzene, not 4-chloro-1,3-dinitrobenzene. Here too, you can see that giving number 1 to chlorine gives the lowest possible number to the substituent nitro group. Also, this compound would be named as 4-ethyl-2-methylaniline and not 2-methyl 4-ethyl-lanilene because E in ethyl comes first in the alphabetical order as compared to M in methyl. When a benzene ring is attached to an alkane with a functional group, it is considered as a substituent instead of a parent. For example, in this case, the alkane with the functional group OH will have phenyl group as a substituent. The naming of the compound will be 3-phenyl 1-propanol. It is important to note that the name for benzene as substituent is phenyl. C6H5, also abbreviated as PH. Fission of a covalent bond. Part 1. To better understand the concepts of organic chemistry, we need to first learn about different reaction mechanisms. In this module, let us first learn about fission of a covalent bond. A covalent bond can get cleaved either by 1. Heterolytic cleavage, by 2. Hemolytic cleavage. First of all, let us understand heterolytic cleavage. In heterolytic cleavage, the bond breaks in such a fashion that the shared pair of electrons remains with one of the fragments. After heterolysis, one atom has a sextet electronic structure and a positive charge, and the other a valence octet with at least one lone pair and a negative charge. Thus, heterolytic cleavage of bromomethane will give CH3+ and Br- as shown here in the equation. A species having a carbon atom possessing sextet of electrons and a positive charge is called a carbocation, earlier called carbonium ion. A species having a carbon atom possessing sextet of electrons and a positive charge is called a carbocation, earlier called carbonium ion. The plus CH3 ion is known as a methyl cation or methyl carbonium ion. Fission of a covalent bond. Part 2. Carbocations are classified as primary, secondary, or tertiary, depending on whether 1, 2, or 3 carbons are directly attached to the positively charged carbon. Some other examples of carbocations are shown here. Ethyl cation, a primary carbocation. Similarly, isopropyl cation, a secondary carbocation. Tetrabutyl cation, a tertiary carbocation. The stability of a carbocation is a determinant factor in many organic reactions. So let us understand about the relative stability of the carbocation. The observed order of carbocation stability is as shown. As you can see, that methyl carbocation is the least stable carbocation whereas tertiary butyl cation is the most stable carbocation. Do you know why? We will find the answers in the following modules. These carbocations have trigonal, planar shape with positively charged carbon, being sp2 hybridized. Thus, the shape of methyl carbocation considered as being derived from the overlap of three equivalent C. sp2 hybridized orbitals with one s orbital of each of the three hydrogen atoms. Each bond may be represented as C sp raised to the power 2 minus H 1s sigma bond. The remaining carbon orbital is perpendicular to the molecular plane and contains no electrons. The heterolytic cleavage can also give a species in which carbon gets the shared pair of electrons. For example, as we can see in the equation, when group Z attached to the carbon leaves without electron pair, the methyl anion is formed. Such a carbon species carrying a negative charge on carbon atom is called carbanion. The organic reactions which proceed through heterolytic bond cleavage are called ionic or heteropolar or just polar reactions. Fission of a covalent bond. Part 3. Now let us understand homolytic cleavage. In homolytic cleavage, one of the electrons of the shared pair in a covalent bond goes with each of the bonded atoms. Thus, in homolytic cleavage, the movement of a single electron takes place instead of an electron pair. Such a cleavage results in the formation of a neutral species, atom, or group which contains an unpaired electron. These species are called free radicals. Like carbocations and carbanions, free radicals are also very reactive. Alkyl radicals are classified as primary, secondary, or tertiary. Alkyl radical stability increases as we proceed from primary to tertiary, as shown here. So here you can see that methyl free radical is the least stable radical, whereas tert butyl free radical is the most stable free radical. Organic reactions which are preceded by homolytic fission are called free radical or homopolar or non-polar reactions. Nucleophiles and electrophiles. In this module, let us learn about nucleophiles and electrophiles. A reagent that brings an electron pair is called a nucleophile. As the name suggests, it has a lone pair of electrons in it. Whereas a reagent that takes away an electron pair is called an electrophile. To better understand the concept of nucleophiles and electrophiles, let us take this example. Here you can see that hydroxyl group is behaving as a nucleophile with a lone pair of electrons. This nucleophile gets attracted towards the methyl group of methyl chloride and attacks the electrophilic center of the compound, which is carbocation in this case. Thus, the electrophiles receive electron pair from nucleophile when the two undergo bonding interaction. Some examples of nucleophiles are the negatively charged ions with lone pair of electrons such as hydroxide HO-, cyanide Nc- ions, and carbon ions R3C-. Neutral molecules such as etc. can also act as nucleophiles due to the presence of lone pair of electrons. Examples of electrophiles include carbocations plus CH3, and neutral molecules having functional groups like carbonyl group or alkyl halides R3CX, where X is a halogen atom. The carbon atom in carbocations has a sextet configuration. Hence, it is electron deficient and can receive a pair of electrons from the nucleophiles. In neutral molecules, such as alkyl halides, due to the polarity of the CX bond, a partial positive charge is generated on the carbon atom, and hence the carbon atom becomes an electrophilic center. Electron movement in organic reactions. Let us learn about electron movement in organic reactions. The movement of electrons in organic reactions can be shown by curved arrow notation. It shows how changes in bonding occur due to electronic redistribution during the reaction. To show the change in position of a pair of electrons, curved arrow starts from the point from where an electron pair is shifted, and it ends at a location to which the pair of electron may move. Let us understand the presentation of shifting of electron pair. In 1, the shifting of electrons takes place from pi bond to adjacent bond position. In 2, the shifting of electrons takes place from pi bond to adjacent atom. And in 3, the shifting of electrons takes place from atom to adjacent bond position. The movement of a single electron is indicated by a single barb fishhook, that is, half-headed curved arrow. For example, in the reaction in the transfer of hydroxide ion to form methanol, the movement of electron using curved arrows can be depicted as shown in this equation.